In this question, it says, an experiment in my research group or in a research group uses cadmium lasers to measure protein movement on a cell surface. In this measurement, the laser is used to excite an electron from the n equals 2 to the n equals 6 state. From there, the electron emits light as it transfers back to the ground state. What is the wavelength of light that is emitted when the electron returns to the ground state in nanometers? And what is the wavelength of light that the laser uses? Draw these transitions. So in this case, we're going to start by drawing, because drawing is simple. We're going to have our energetic states, and they decay in size, so everyone gets closer by about 50%. And so we have n equals 1, 2, 3, 4, 5, and 6. And so we know that our electron goes from the n equals 2 to the n equals 6, and then it's going to come back down from 6 to 1. So this calculation, and I'm going to give you the answer for both, but I'm not going to calculate both of these step by step. So we're going to start with the transition from n equals 6 to n equals 1. So in order to calculate this, we know that this blue arrow corresponds to delta E. And we know that delta E equals negative 2.18 times 10 to the negative 18 joules, 1 over nf squared minus 1 over ni squared. And once we have delta E, we know that that's the energy of a photon. So E photon equals h nu. And if we're looking for wavelength, it also equals hc over lambda. So you could rewrite this to be lambda is equal to hc over E photon. And E photon is equal to delta E in this case. So now we have this information. This calculation can be complicated if you're not sure which equations to use. But h and c are Planck's constant in the speed of light, so really we just need to calculate E photon. So E photon, in this case, is going to be negative 2.18 times 10 to the negative 18 joules, 1 over 1 squared minus 1 over 6 squared. And that gives me 2.11 times 10 to the negative 19 joules. So lambda is equal to 6.626 times 10 to the negative 34th joule seconds, multiplied by 2.998 times 10 to the 8th meters per second, divided by 2.11 times 10 to the negative 19 joules. And then in 1 meter, there's 1 times 10 to the 9th nanometers. And so if you plug this in, I get 93.7 nanometers. Now you might be asking yourself, why does that have 3 sig figs when there were no real sig figs in the problem? For a graded assignment like an exam or other things, I would just ask you, it would say in the problem 3 sig figs or 4, however many it was I wanted. So this is the answer to the final transition. And so I know I said I wouldn't do it the other part, but I am going to go ahead and do that for you. So for the excitation, in this case, it's the exact same calculation, where for the excitation, we have E photon. In this case, we're actually going to start with delta E, is equal to negative 2.18 times 10 to the negative 18, 1 over 6 squared minus 1 over 2 squared. And that gives you negative 4.84 times 10 to the negative 19 joules. Now in this case, for excitation, delta E equals negative E photon. It's just really going to get rid of the negative sign, but this has to do with thermochemistry, where we can see that the change of energy is inversely proportional. So lambda is going to be 6.626 times 10 to the negative 34th joule seconds times 2.998 times 10 to the 8th meters per second divided by 4.84 times 10 to the negative 19 times 1 times 10 to the 9th nanometers in 1 meter. And this gives you 410 even nanometers. Again, the value in the problem up here, it would say use 3 sig figs. And this is how you do this calculation.